So let's recap where we've been so far. We've talked about the idea that scatter plots are a good way to eyeball the relationship between two variables. We then looked at the different types of relationships that can exist between variables, such as a positive or a negative relationship. We then stepped away from scatter plots and looked at the Pearson's correlation statistic or correlation coefficient, which is a correlation statistic that gives us a mathematical relationship between two variables. We then looked at the R squared as a measure of the variance in one variable that explains the variance in the other. Now, bivariate correlation is used when the researcher wants to measure the relationship between two variables. But the accuracy of these correlations depend on a few things. So some of the things to look out for are linearity, homoscedasticity, restricted range, and outliers. So I want to go through some of these assumptions of the linear correlation coefficient right now. So one assumption of the correlation coefficient is that there's a linear relationship between the two variables that you're looking at. Now, most of the time we're interested in linear relationships where the trend in the scatter plot follows a linear path. However, there are other types of relationships where the pattern does not follow a straight line. Here's an example of a curvilinear relationship of stress/anxiety and performance, which could be exam performance, sport performance, or really any type of performance that you have in your life. Now, when anxiety or stress is low, it may be hard or motivated. It'd be hard to get motivated or even hard to get out of bed even. So it's likely that your performance is not going to be great. Now, as stress or anxiety goes up, so does the performance until it plateaus at some point. After this point, anxiety is too high and it becomes increasingly difficult to perform. And you often see this in TV, where there's some sports people who seem to choke in pressure situations. In other words, their performance drops and usually drops quite dramatically. So using the linear relationship, which is what the Pearson correlation coefficient is, with a pattern like this, that curvilinear relationship, would show a relationship of close to zero because it can only deal with a linear relationship. And this would clearly be misleading. So you should always examine the scatter plot to see what the relationship is between the two variables before deciding that the Pearson correlation is appropriate. Alternatively, let's use another example. I could use the example of age and memory. As age increases, memory increases until a certain age when it starts to plateau in probably mid to late adulthood. Then as age increases after that, memory starts to decline into old age. So again, using the linear relationship, which again is what the Pearson correlation does, with a pattern like this, you would expect the Pearson R to show an almost zero relationship because it can only deal with a linear relationship. Again, this would be misleading. So again, you should always examine the scatter plot to see what the relationship is between the two variables before deciding that a Pearson correlation is appropriate. Another assumption is restricted range. So we also have to be careful we don't have restricted range, as this could be misleading. Low Pearson correlation coefficients may arise even though there's a strong relationship when the range of scores in the sample is much smaller than the range of scores in the population. So in other words, it has a truncated range. Now let's look at GPA and entry into honours, for example. The relationship is graphed in the following picture. However, now I don't know about you, but this looks like a bit of a snowstorm to me. There does not appear to be any relationship between GPA and entry into honours. However, students in the honours program do not represent the full range of GPA scores. Those with the low GPA scores are not included here. What effect does this restriction of range have? Well, if I have to look at the following figure, that includes the full range of students with a GPA. This shows a positive relationship. So unless you recognise that your sample of honours students are have truncated the range of GPA scores, you might be tempted to dismiss GPA scores as worthless. Now, an assumption of the correlation coefficient is also the assumption of homoscedasticity, or equal, being what homo means, and spread, skedasticity, which means equal variance. So this means that the distribution should be equal across the range of scores on the x-axis. In other words, when you look at a scatter plot, there is approximately even variability in the scores and they don't fan out at the extremes. If fanning out does occur, then homoscedasticity assumption could be violated and we have something called heteroscedasticity. And this could also be due to non-normality of data, which we might want to check out as well. Now, outliers is another example that, or assumption that we need to be careful of, and outliers are an extreme score or a group of scores and are also something that can distort the correlations. Now, whatever action you take with outliers, it needs to be reported in your results section. What assumption problems are evident here? Now, there are two that I can see. Note that there's an outlier. It's not actually extreme on either variable. It is the lowest score, but not excessively so on the number of work hours. But there are 3 other scores actually equal to it on the y-axis variable of stress. However, it shows a clearly deviant relationship between the variables. You can also see this relationship between stress and work hours, which is heteroscedastic. Much greater variance at higher work hours than at low work hours. In reality, it can be much more difficult to detect outliers and heteroscedasticity, so you may need to draw on other people who have more knowledge around correlational research.